Hello, welcome to Coffee Break with Microchip Technology. Coffee Break is our forum in which we discuss new and evolving technology, all in about the amount of time it takes to drink a cup of coffee. I'm your host, Eric Glatfelter. Joining us as usual is Aliyah Fahout. Aliyah, would you give our audience an overview of how they can interact with us today during the live stream?
Yes, of course. Thank you, Eric. Well, hello everyone. Thank you for joining us today. We are currently live on YouTube, Facebook, and LinkedIn, and you can participate in today's episode by leaving your questions and comments in the chat below or emailing us at livestream@microchip.com after the broadcast. Don't forget to follow, like, and subscribe to our social media platforms. Back to you, Eric.
Thanks, Aliyah. Our topic today is IoT-Enabled Smart Access Control, and joining us is Alden Doyle, a machine learning engineer here at Microchip. Alden, welcome to the program.
Thanks, it's great to be here.
All right, so there's a lot going on in edge computing, AI, and machine learning in the industry, and also certainly here at Microchip. So why don't we start? Can you give us an overview of the SDK we want to talk about today and how it can help design engineers as they work to enable IoT applications?
Absolutely. So I'll talk a bit about the VectorBlocks SDK. So in the machine learning world, there's kind of been a gap between the tools that engineers use to create machine learning models. So these are the ones on the left, like PyTorch and TensorFlow, and then the embedded processors where they want to put them on, especially for edge use cases. So this is the Microchip solution for this problem, especially for PolarFire FPGAs. So this is the SDK that can take models from any of these machine learning frameworks, import them to our format, optimize them for inference only, quantize them to 8-bit integers so they can run much faster, compile them for our accelerator, and put them on the FPGA. And then also there's the actual accelerator that runs on the FPGA fabric that is optimized for PolarFire. So we try to make a system that is really easy for users to just take their models from existing frameworks and put it on our chip and with minimal effort.
Okay. So you mentioned AI inferencing there. If someone were to want to implement that in an FPGA, what would be some of the main design considerations?
Yeah, sure. So first is the ease of use, and that's kind of what I talked about in the SDK of how hard it is for customers to put their models on the chip. Next would be the flexibility, and can you run multiple models and swap things in and out? And with our solution, you can definitely do that. Next would be concerns about the resources versus the performance. So how much FPGA resources does the solution require? So, we already have an IP accelerator that's optimized for PolarFire, so you get a good range of options in terms of how much resources versus how much latency you want. And then finally, once your solution is ready, it's a question of how much performance do you get versus the power. So PolarFire FPGAs are really great in that realm. So good for edge AI use cases where you really have power constraints and power budgets.
Okay. So talking about power budgets, obviously power budgets can be tight anywhere, but particularly in IoT applications, they may be especially tight. So how do the PolarFire FPGAs compare to other options that are available on the market?
Yeah, so this chart kind of goes over a pretty good comparison, I think. So the first two bars on the left are a competitor to us on FPGA. And the right three bars are PolarFire FPGAs. We have three different sizes of accelerators with different trade-offs of performance versus resources. So that purple number in the purple box is a measure of the performance in giga operations per second. So we just tried to find some that are kind of in the same range. But those bars are the power consumption. So the blue part is the static power, red part is the dynamic power. So you can see that for similar performance numbers, PolarFire is consuming far less power. This chart shows 2 to 3 times more power efficient. And if you look at the static power, it's close to 10x more efficient, and dynamic power is close to about twice as efficient. So a large advantage for those applications that are power constrained.
Yeah, a very large advantage. What is fundamentally behind that?
It's really that the PolarFire FPGA is made with non-volatile RAM versus SRAM of competitors. So by design, it has a huge advantage there.
Sure. Okay. Okay, well, great. So can you give us an example of how this might be used within a larger IoT example?
Yeah, of course. So at Microchip, we're known for microcontrollers and microprocessors, but it's kind of fun working here because we have a broad range of chips and solutions. So this is a demo made with FPGA, motor control, Bluetooth, Zigbee, wireless, kind of all put together for one interesting solution. So we actually have a video kind of showing this in action. It's a toy garage door right there, controlled by a low voltage motor control chip. And right there is the FPGA kit with a camera that will do face recognition. And if it recognizes the user of this, it'll automatically open the garage door. There's also a Zigbee and Bluetooth wireless chip. So you can control through your phone over Bluetooth the garage door also. And through Zigbee voice control, you can also control it through an Amazon Echo. So kind of a cool use case of a lot of different uses of IoT.
Yeah, very interesting use case of what we think of as IoT. So, all right, so that seems like a very robust and pretty complete solution already. Are there enhancements underway for VectorBox?
Yeah, definitely. So we're always working on new stuff. So over here on the left is the Smart Embedded Vision Kit. That's what we have out right now. So it's already set up for use with a MIPI camera, HDMI input to outputs. You can get started on your embedded vision task. Our software development kit has a ton of tutorials for different models already supported. And the existing project in this has demos like face recognition, gender and age estimation, object detection, image classification. So kind of trying to support all of the common use cases of computer vision AI. So on the right, we have our newer FPGA, PolarFire SoC. So SoC meaning system on a chip. So this one has 4 hardened RISC-V processors. So you can do a lot more in software along with the FPGA. For instance, you can run Linux on this, so it can make things easier to develop. And this is also an embedded vision kit, and so we'll be rolling this out with a lot of updates. So native use of TensorFlow Lite, a bunch of solutions such as license plate recognition, pose estimation, lane detection, and then a version for space with triple redundancy.
All right, a lot going on with the VectorBox SDK, a lot going on with machine learning. Thanks for the overview, Alden. Very interesting. At this point, let's go to Aaliyah and see if we have any questions from the audience today.
Yes, we do. I do have a question that we received from LinkedIn. Can face recognition be done by FPGA?
Definitely, FPGA is a good use for that. There's kind of two models going on there: a face detection, which is finding the face and the key points, and then another follow-on one for recognition, which takes the face and turns it into an embedded vector. And you can quickly compare that vector with a database of how many faces you've seen before. So you can recognize people from a database or just compare, like, have I seen this person before? So pretty good use case for us.
Great, thank you. I do have another question for you that we received via email. What do I need to get started with vector blocks?
So our software development kit is available on GitHub. You can find it there. Just search for vector blocks. Also, we have Smart Embedded Vision Kit, so a board with a project that you can load up, so you can actually get started on this fairly easily. So you can swap in and out models and control them through C code, and basically update your design without ever having to get started on the RTL part.
Great, and I have another question that we received in our emails. When will vector blocks be supported in PolarFire SoCs?
So we're working on that right now, and we expect that to be out in the first calendar quarter of next year, so early 2023.
Thank you. And which frameworks does vector block support today?
So we've been trying to support all the popular frameworks, at least in the computer vision space. So that includes MXNet, Caffe, DarkNet, PyTorch, TensorFlow, and probably some others.
Thank you. And which I think I already asked that one. What solutions are available today?
So right now, our demo includes the face detection and recognition, age and gender, object detection with, I think, YOLO models. So that's a find object, kind of find where it is, draw, isolate that, and then characterize or classify which model that is. Along with just general image classification, sort of like your ResNet models.
Awesome. And why FPGA compared to Raspberry Pi?
Compared to Raspberry Pi, usually you get more throughput on FPGA. With, say, Raspberry Pi, for the applications that we're looking at, like face detection, you might be able to get 1 or 2 frames per second, but with FPGA, you'd be looking at 20 to 30. So it's really a matter of throughput for that application.
Thank you, Alden. And I have another question that we received in our emails. Where do you see Microchip FPGAs being used?
Good question. So we get a lot of use in defense due to our military-grade security features. Also, a lot of applications in space due to radiation tolerance parts, and then a lot of industry uses, mostly due to our low power. So really useful for edge AI in those cases.
Great. I can try to do a few more. Where can you see your memory?
Where can you see your memory? I'm not sure I understand this question.
Let me see if I can expand on that. Let's try this one. How is it similar with other FPGA platforms?
A lot of vendors are coming out with tools like this to accelerate your models. With regard to memory, usually the model is stored in DRAM and streamed onto kind of a generic accelerator. Ours is optimized for CNN models, which is a type of neural network that's popular in image processing. So that allows you to kind of stream in any model you want to use. So for instance, in the face recognition, we use multiple models in series. So you can switch models on the fly in that way.
Perfect. Can FPGA improve computation for 3D reconstruction?
Yeah, definitely. We don't have a tutorial for that at the moment, but that is kind of a popular application in computer vision right now. So I think that looking at kind of the sizes of those models and the computational requirements, they could fit on FPGA would be a good target for that.
Awesome. Okay, I can do one more question for you, Alden. What language is used to write code for face recognition, VHDL or Python?
So both is the answer. The IP accelerator, that has to be written in VHDL or Verilog. But a lot of the control for it is in C code. So there is a RISC-V processor controlling the accelerator through C code. So a lot of your development can be done in C, and you can be controlled that way. So that makes it easy. The software development kit, though, starts in Python, which is the most popular language for machine learning right now. So all of the TensorFlow and PyTorch frameworks have a Python interface. So you'll use that with the SDK.
Well, thank you, Alden, for answering our viewers' questions today. If you have additional questions or comments, you can email us at livestream@microchip.com. And back to you, Eric. Thank you.
Thanks, Aaliyah. Alden, thank you for joining us and sharing some of your expertise. And most of all, thank you to the audience for your time and all the great questions today. For more information, visit us at microchip.com/coffeebreak. There you can see our schedule of upcoming episodes. You can add episodes to your calendar, you can sign up for notifications, and you can peruse our library of previously recorded sessions. Thank you again for your time. See you next time.